Hello, welcome to Engineers Ireland. What we'd like to cover today is the geometry of the circle. The last one of these was the geometry of the line, and it seemed a bit long. It's longer than most of the other ones. However, it's long because many of the concepts that are in there I wanted to spend a bit of time because they actually also come up in the circle. So hopefully this will be a short one. Now, to start with, the circle pops, the basic equation for a circle pops out of the Pythagorean triangle. If we draw a circle, and here's the radius up at some angle or another, and we'll say the point that it's touching is x, y. What we know is when we go to the end of the radius, the tip of it, and draw a line parallel to the y-axis towards the x-axis, we've made a right angle triangle. Now, that means that length here, just out to this, is x, and this height is y. And Pythagoras tells us x squared plus y squared equals r squared. So the fundamental equation for a circle where the centre is at the origin is just a statement of the Pythagorean theorem. Obviously, there's lots of nice little interesting things you can learn about this. And to begin with, in these chapters, what they really are wanting to do is to introduce you to a number of concepts, and one of the concepts that they'll want to introduce you to is a tangent. Now, if we pick a tangent at a point on that circle, obviously drawn to perfection here, we'll say it's touching just there. A tangent just touches the circle at one point, no more than 1 point. And the interesting thing about the tangent is it's always perpendicular to the radius at that point. Now what that means is once I know the slope of the radius, which will be the y value divided by the x value, I'll know the slope of the tangent, because when two lines are perpendicular to each other, the slope of one multiplied by the slope of the other is equal to -1. You've been aware of that now for at least 3 years, so thankfully this is not new stuff, it's just restatement of old stuff, okay? That's all very good, but not all circles have their origin at 0. We can now go along and generalize this basic equation that we have written up here, this one. And to generalize it, what we will do is we'll move the origin, and we'll say what I have now is this centre of my circle is going to be h, k. And now here's my x-axis and there's my y-axis. So the good news is that point now, hk, is not at the origin, so we're in a position to start playing and finding out new stuff for ourselves. That point, x, y, this is x over here. We also know that all the way out to here is h. So we're saying, this horizontal bit here is the same as that horizontal bit down here, and that has to be x minus h. Okay? The exact same thing applies for the y's. That's k. That's y. and we're saying this little bit here is all of the y minus the k, and that bit there is exactly the same as that bit here. So what we have in this location is y minus k. I now know that length, and I know the horizontal length, and they're still a Pythagorean triangle. So what we have is x minus h squared plus y minus k squared is equal to the radius squared. Clearly, when h and k are 0, the centre of the circle is at the origin, and this second equation here just simplifies down to the first equation. So the first equation is just a very specific case of the second equation. All of this makes lots of sense, okay, and it's still just Pythagoras. The only thing we have appealed to here is the relationship between the three sides on a right angle triangle. There's a lot of questions in the chapter relating to this basic equation, and the whole idea is just us to get you used to using it. Now, the third equation that is used is the one that I actually don't like, and I don't like it because we have now happily started with the most fundamental equation, this one here, built it to the second one, and then people go along and they change it. And they change it to the one I'm showing down here at the bottom. And what I want you to notice is the letters have changed. You've got a G and you've got an F. Whereas up here, you had a H and you had a K. I much prefer to multiply out this first equation up here, and what you'll get is x squared minus 2hx, okay, plus h squared, and you get plus y squared minus 2ky plus k squared equal to r squared. So that's x squared minus 2hx plus h squared plus y squared minus 2ky plus k squared equal to r squared. Now, if we bring it into the form that'll be similar to the one down at the bottom, we will get x squared minus 2hx plus y squared minus 2ky plus c equal to 0. And the c is pretty obvious. Now, technically, this equation is identical to this equation down here. But why I prefer it is because it still keeps the minuses. And by keeping the minuses, we're back and we're still just using the same graph that we have over here. We normally graph our functions in the first quadrant, and we expect our values to be plus up there. So h shown as a plus h, k shown as a plus k makes a lot more sense to me than the graph that is normally put beside this third equation, because when you see it plotted, you will have a minus g and a minus f up in the first quadrant, and I've always thought it's a bit foolish because minus g will always have to be a negative number then. I prefer this version. I actually don't care which one you use. I'm just saying to you, this third one here is a natural progression from the second one, and I actually think for the mind it's much easier to see its relationship to the center of the circle, and it's identical to the second equation. Clearly, with the exact same relationship for finding our r, it's still the x component of the centre squared plus the y component of the centre squared minus the c, which is the free term. Okay, it's still the same equation. The only thing that's different is I like to leave in the two minuses. Okay, and as I said, I don't mind which one of the versions you use. I'm just showing you that this third one is only a natural follow-on from the second one. The interesting thing is, once you get to this point, you get to something that was covered in the line, and that is the locus again. And as mentioned when we were looking at geometry of the line, locus is very well described in geometry of the line, because normally you expect to get to that before you go on to geometry of the circle. And I'm just saying to you, read back geometry of the line when it's talking about locus. Really what a locus is, it's a rule, and that rule means that some things will belong to the club, in other words agree with the rule, and other things won't. And those things that belong to it generally form a shape. It could be a line, it could be a circle, etc. And what we had for the line, and I'll draw it over here, that the length between a point P and a given point A was equal to the length between the same point P and a second point B. So we're saying one length was equal to the other one, and A was a given point, B was another specific point. What you do with these things is you let P equal to x, y, and you plug it into the distance formulas. The one that's given for the circle is almost exactly the same, so there's a very good overlap between the two of them here. Now it's interesting, and it's actually worthwhile playing with this, okay? Just giving the little example that's given in the book, because I just want you to see something. The example is and we're going to let P equal to 0 equal to xy. So what we will get from this is that PA, which is equal to twice the square root of so it's equal to 2pb. And all that breaks down to, when we square out both sides, what you will find is x squared plus 2x plus 1 plus y squared is going to be equal to 4 outside of x squared minus 4x plus 4 plus y. I don't intend to go on beyond this in the writing of it, because what I want you to notice is on the left hand side there's a single x squared and a single y squared. Unfortunately there are 4 x squareds on this side and there are 4 y squareds. So what it means is we will finish up with an equation where we will still have x squareds and y squareds left. You'll have this many of them. 3x squared plus 3y squared minus 18x plus 15. So we're saying, because I still have squared values in the x and the y, the answer here is a circle. If we go back to the examples given for the line, over on the right hand side here, PA equals a single PB. It's just PA equals PB, whereas for the circle we were given it for 2. While it was a single PA PB, when we worked out the distance formula from P to A and similarly from P to B, what happened was the x squareds cancelled each other and the y squareds cancelled each other, and as such then we were left with an equation where the most x was to a power of 1, and similarly for y, so we had a straight line. So in these rules that we're looking at here, the PA equal to any number multiplying into the PB, any number except 1, you're going to get a circle out of this. Over there in the line, in the example that was given to us, it was PA equal to 1 multiplied by PB, and under that case, under those circumstances, you actually get a line out of it. But fundamentally, all this piece of maths is exactly the same in the line as it is in the circle. So that's good news. Now then, let's go back to the equations. And I'm saying that, well, you could write that as x squared minus, or sorry, we'll give the y's first. You can do it that way, or the way that it's given in the book is x squared plus y squared plus 2gx plus 2fy plus c equals 0. The only fundamental difference has to do with when you graph it. Using this method, the center is hk, and using that, it's minus g minus f. Now I'm just intrinsically opposed to using a minus of a letter up in the first quadrant, because the g has to be the g position and the f position in the first quadrant, the center of the circle. The values in the first quadrant must be pluses, so they're being recorded as minuses in g's and f's, and I've never liked that. I think it leads you to having to double think what the centers are. So in any particular equation, if we have, let's find one in here. The minus 2, and you'll notice the minus 2h would tell you immediately that h is 1, and this one will tell you that k is minus 1. Okay? I just find it easier. You can use the g and the f version. It doesn't bother me. What little things do we know that can help us solve the kind of problems that they give? Now, again, these equations are straightforward. The basic mathematics is straightforward. So how they try to make it more complicated is they give you equations where some constant is unknown, or maybe even two constants are unknown. But there's a few little rules that are well worth seeing in here, and they are when the circle touches the x-axis, and when the circle touches the y-axis. In Rowntree book it's all worked out, but fundamentally what it's telling you is that in the basic equation that they have, and I'll use it his way first, well actually I'll just leave it his way, we're saying minus g minus f. Under those circumstances where it's touching the x-axis what can you say? Well, right here, when the radius is perpendicular to the x-axis, you're saying the radius is touching the x-axis and it's at the center. So I know something. I know that height is the same as the radius. When it's touching here, it's perpendicular to the x-axis, so the radius length, I know the radius length. HK for the center. In this case we would be saying, when it touches the x-axis, that height is k. So the radius we can find out. Similarly down here. Now the two equations that are that he has given are g squared is equal to c, and that happens to be exactly the same as in the case that I'm talking about, where h squared is c, and the other down here which is the same in my case as k. So the two systems are almost exactly the same, the g and the f and the h and the k. The only real difference is when you're looking at the basic equation, it's so much easier to work out the center of the circle if you're looking at 2hx and 2ky rather than minus 2gx and minus 2fy. These two little equations, whichever half you play with, whether it's that half or that half, are really useful, because what they allow you do is they allow you to take a shortcut. Most of these questions with the circle will give you three pieces of information. If one of them is that it touches the x-axis or it touches the y-axis, you should be able to immediately trot out this equation, and that will allow you, it gives you one of 2 or 3 equations that you're going to build up very, very quickly. The next thing that this section covers are parametric equations of a circle. Now again, we actually had to look at this, the parametric version, in dealing with the line, only we weren't told we were looking at a parametric version. When we were working out the angle between two lines, we had to go and figure out that the distance was equal to r sine theta. Now that actually is a parametric version, and you will find that the maths is very clear on this, and it's very simple. Let's once again draw our unit circle, and this time I'll draw the radius much longer. For the unit circle I got 1 minus 1 minus 1, 1. And what we know for the unit circle, given that that's theta, we know that this length is cos theta and that length is sine theta. Now look at this longer line here, which is r, the radius, or whatever length that you're actually looking for. Because we're dealing with a circle, we're going to call it r, because obviously there's a much bigger circle that we're looking at out along here. We have set up two similar triangles, a 90 degree and a 90 degree. They both share theta, and it means that that angle then must be equal to that angle up here. These two are the same. 3 angles the same in each of them, they're similar triangles. My radius in the unit circle obviously is 1. So the ratio all the way along on the radius up along here is r is to 1. One is r times bigger than the other. Because of that, I know that the same ratio holds for the other equivalent sides. This one is r sine theta, and this length out to here is r cos theta. So what we've said is that length here from the center of the circle, this vertical length here, okay, which is related to the center of the circle, and we could say the center of our circle is h and k. Now here's an interesting thing. In this section in the geometry of the circle, we're back using h and k again. It's not g's and f's. So another reason why I don't like the g and f formula and I prefer the h and k version is because later on in the chapter you're back still talking about h and f versions, h and k versions. So let's call the center of the circle h and k. Center h, k, same as you saw before in the second equation for the circle. That means that somewhere down along here we've got an x-axis and somewhere over here we have a y-axis. Now if I want to measure this point on the big circle up here, up in the top right hand corner, which is an xy point, I'll say there it is, this is my x, and similarly up on the top of the diagram here, that's my y. So what's my x made up of? It's made up of two bits. It's made up of the bit coming out from the origin to here, and I know that length is h. It's also made up of this bit which brings you from h across to the x, and we know that that bit is r cos theta. So x equals h plus r cos theta. Nice and handy, you're just adding two lengths. Let's look at the y bits. I know, going from the origin all the way up to here, that length is k. It's the y component of the center of the circle. I also know that length, because that length is identically equal to the vertical side of the right angle triangle that I have. So that bit up there is r sine theta. So we now can say y is k plus r sine theta. Now all that means is that we have two ways now of talking about points on a circle. One of them is to talk about it as x's and y's, and if we talk about it as x's and y's, we will finish up with our three algebraic expressions, you know, the ones, let's say, like the x minus h squared plus y minus k squared equal to r squared, that algebraic expression. We could finish up with that. The other way is we can say that x is h plus r cos theta and y is k plus r sine theta. Interesting thing about them. Let's look at an example. If we go x equals 2 plus 3 cos theta and y equals 1 plus 3 sine theta. Now, by the way, we can interchange cos or sine here because it all depends on where we call the theta. Okay, it doesn't make much of a difference. Our x could have the sine in it and our y could have the cos in it. That doesn't matter. It's still a trigonometric way of expressing the circle. Now, there's a few things that are important. If you were told that this is a parametric version of an equation, for you to know that it's a circle, something must happen. And what must happen is that that number here must be the same as that number there, because if you go down to the bottom right hand side, there are, they must be r. So I can tell you now that for this parametric version the radius is 3. See how easy it works? It's very simple once you get used to it, and it all works on the unit circle, which brings you into trigonometry to define what cos and sine is, and that right angle triangle and the larger right angle triangle belonging to a radius of r, which will give you r sine as the one side and r cos as the other. So we're happy with it. And the other is, if you've cos in one here, you'll have sine in the other there. Once we have that, we know we're dealing with a circle. Here's the other really nice thing about this. That's the x component of the center of the circle, and that's the y component. So it's actually a handier way. And the reason why it's a handier way, circles are curvy things, okay, not straight lines. Curves are more easily expressed using trigonometry than using x's and y's. X's and y's are kind of an unnatural way to try and express curved shapes. There's a second type of algebraic expression that's used. For example, they could tell you that x equals 2t all over 1 plus t squared, and that y is equal to 1 minus t squared all over 1 plus t squared. I'm mentioning this one because what you've got to understand is, if we're actually dealing with trigonometry to give us this polar coordinate system, then most of these parametric versions for a circle you would suspect come from trigonometry. And if you look at those two equations, if we look at trigonometry, we will find that sine of 2 theta is equal to 2 and so that little t, every place it's expressed in our xy equations, in reality stands for tan theta. So it's nice and handy. Again, these equations all break down into being trigonometric expressions. The difference with these particular ones is you will notice that one of them has just a t to the power 1 at the top, and the other one has a t squared at the top. Now, Aidan Rowntree is actually very good in his discussion on these particular ones, and what he tells us is, if you want to eliminate out the t, he says start with the t squared equation. And the reason you start with that one is because everything in this equation over here on the right hand side, all the t versions are all t squared. So we'll get a nice simple expression for its relationship with y. Whereas if you start over on the x one, because you've got a t squared at the bottom and a t to the power of 1 at the top, you're going to finish up with a more complicated expression. So whichever one has the square at the top, that's the one you use to express t in terms of the x or the y. Okay, in this case it's the y. Okay, and once you do that, it's easy. If you do the other way, it's actually hard. That's the key, is to remember to express t in terms of the variable that has the equation with only the t squareds. When you look at the subsection on touching circles, you will find that there's two ways for circles to touch. They can do it externally, or they can do it internally, like that. Now, The interesting thing is there are equations, and we'll just say for the moment that is R1 and that's R2, and we'll go R2 and R1. Just so you'll be clear, that's the center of the smaller circle, that's the center of the bigger circle, that's the center of the small one, and that's the center of the big one. Okay. For us to prove that circles touch, what we want to do is to find out the length between the centers, because if the length between the centers, D, if it's equal to R1 plus R2, if it's exactly equal to the two radii, well then they touch, and they do so externally. The other is if D is equal to R1 minus R2. Now be careful, because if you've used the small r first, you could finish up with a negative number, and distance is always positive. So because of that, we do use the absolute value here. So whatever the answer that comes out of this, we're going to make it plus, because the distance is always positive. And if this is the case, it'll happen internally. And the nice thing about it is, what do you think the two equations are in relation to this? We've come across them before, and where we came across them was the finding a point C which sits between an A and a B point. This was in geometry of the line, and it sits in with a certain ratio. Remember, it was R and S. So there was an internal one and there was an external one. Okay. Now if it touches externally, okay, where you have a plus in here, then you're going to be using the ratio relationship that had the pluses in it. Okay, so that one up there, we'll just bring it down and I'll just show you the x bit belonging to it. You've got S x1 plus R. Okay, that was the internal one. Okay, and the other one has a minus, so we'd be talking about the minus version. That's just the x version of it. Okay, that's all we're doing. We're just using ratios. And you say, what are the ratios? Oh, guess what? That guy and that guy. Where is the point C that we were talking about? It's this one. So you will notice this external one has an A, it has a B, and it has the point C to relate you back to your geometry of the line. And the nice thing is that equation is actually in the logbook, so you don't have to worry about it. Here, when we're dealing with the circle and we're dealing with touching externally or internally, we're just using this divisor of a straight line segment into an R and an S, and in this case it's an R1 and an R2. It's exactly the same sort of thing. The second half of this chapter is really devoted to tangents. Everything up to this really had things to do about circles, whether they're touching or not, etc., or different types of equations for them, or do you write them in a parametric version. The second half is like, it literally is a part 2. Tangents are always perpendicular to the radius at the same point of the circle. Okay? There are quite a lot of what we'll call cute little rules in relation to these. So what I'm saying to you is, it's really important that you read your chapter on this, because, for example, Aidan Rowntree has several guiding principles that he gives you. Those guiding principles are the ones that will let you know which version should I use. Okay, for example, one piece of advice that he's giving, and most of his advice is given by way of notes, and I'll just read it straight. If we are given the equation of a line and the equation of a circle, we can investigate if the line is a tangent to the circle by either. In other words, he's saying there's two possibilities, two ways of doing it. One is solve between the equations and see if there is only one point of intersection. Obviously, if they only touch at one point, you do have a tangent. So that's one way of doing it. What's the second way? Check if the perpendicular distance from the center of the circle to the line is equal to the length of the radius. Now again, you'll notice this is just straightforward geometry of the line. We're saying, there's a line here which we'll call the tangent, and the center of the circle we'll say that's a point, and you look for the perpendicular distance, and when you find that the perpendicular distance is exactly the radius, you say yes, that line is a tangent to my circle. So which one do you use? Okay, and this is why reading the book carefully is so important, because he explains why. He says, in theory we can use whichever method we choose, but in practice we would prefer to keep the amount of work to a minimum. And that's certainly important, because in the exam you are playing against time, so you don't want to be wasting it. So what's his piece of advice on this? The method we use depends on whether or not we want the point of contact. If you were asked in the question, prove that this line is a tangent to the circle and find the point of contact, then he's saying to you, we use one method. If we do not need the point of contact, okay, we use the other method. The point of contact, you use the first one. And the reason for it is, if you solve between the two equations, you're going to get an x value and a y value. Therefore, you've got the point that they meet at. Whereas, if you don't want to know the value of the point where they meet, all you're looking for is the perpendicular distance correct? So that second method is the one you should use when you don't need the point of contact, and the first one is the one you should use when you do need the point of contact. All straightforward and clear. Lots of advice like that in the chapter, okay? Now, most of this stuff is very easy. There is one theory or theorem with a little proof that can be asked in the exam, and it has to do with the tangent formula. Now, the tangent formula and that is where our circle is, and the point is x1, y1. First thing you notice, because we're using this circle equation, this formula only belongs and should be used where the center of the circle is 0, 0. Okay. Now, in reality, you could use the two other ones, but what you'll have to do is translate your circle if you want to. And you can translate it across so that its HK center now becomes the origin, and then you can apply it. But in general, you're just asked it in relation to the simple basic circles. Here's the beautiful thing about this. The proof is really simple. Let's draw it. Radius length, well, we'll call it r. That's r. This is my tangent, okay, and they always meet at a right angle. So if they always meet at a right angle, if I continue my tangent until it meets the x-axis, I've got myself a right angle triangle. It's just not rotated the way you'd normally see it. Okay. So then, what's the proof? We know the center. Is 0, 0. Now, What's the slope of the radius? That length is x and the height is y. Okay? For a given point, we will say this point here, it's x1, y1. You notice that we are dealing with that point x1, y1. So there it is there. And we're saying, slope. You'd say, what is it? It's the y height divided by the x. It's the delta y over delta x. So it's y1 over x1. We know the slope of the tangent because it's perpendicular to it. Remember the basic equation I'll draw down at the bottom. m1 by m2 equals -1. So slope of tangent is equal to minus x1 over y1. It just comes straight out from that little equation down here. So now, let's plug that in to the equation of a straight line. And what we'll get is y minus y1 is equal to minus x1 over y1 by x minus x1. And when we simplify that down, we just get and that's equal to r squared, which is what we looked for up at the top. There's absolutely nothing in this proof other than to recognize that you have a right angle triangle first off. You can create a second right angle triangle once you drop this here and you say this is my x1, it's the x coordinate of the point I'm interested in, and you're just using the slopes of two lines perpendicular to each other. So there's no problem with that one. The other type of thing, now by the way, there's a very clear connection again between the circle and the line in the two tangents to a circle from a point outside the circle. So we're saying I have a point over here. I want to find the two tangents belonging to that circle. Now, what can you do about this? One of them is, if you know the center of your circle, guess what? You're going to use the perpendicular distance formula here, the same way as you can use it here to that one. Oops. This is not as easy to draw on as you might think it is. So we're using its perpendicular distance formula. Now, interestingly enough, in Aidan Roundtree's book, in the line, he has exactly the same problem in it as he has over here, where he's looking at a perpendicular distance from two lines that cross at a point. The only difference is he didn't draw the circle in it. It is virtually a carbon copy of the stuff that's in this particular one. So what do? We say, okay, that's one of the things I can use, the perpendicular distance. What's the other? Some other piece of information is going to be given to you. It could be that, well, first off, you'd be given the point. That's one thing that you will know. So you'd say, I can use that point to come up with the equation of a line. And it will be in the form of, let's say, if this is x1, y1, we'll say it's the y minus y1 equal to m outside of x minus x1. You can use that equation. So you come up with, having plugged in whatever the y1 is and the x1 is, you finish up with an equation then that has an m in it, the unknown that you don't understand at the moment. Then you appeal to the perpendicular distance to come up with a second equation, and you solve between the two equations, and out will pop a line equation with x's and y's in it. There's just one last. Now, by the way, all those questions are extremely similar. They'll only change basically the kind of numbers that you have in the lines or where the point is, but it's fundamentally the same kind of stuff. It is well worth your while practicing several of the questions on this. And once you do, you're only left with one last little bit in the chapter. The last bit is extremely similar to another piece of geometry of the line. When we were looking at concurrent lines, if we had two lines, I'll draw it over here, this is just a line bit. If you had L1 was equal to 0, the other line you can call L2, and you have a whole load of equation, and this would be A1x plus B1y plus C1 equal to 0, and this is A2x plus B2y plus C2 equals 0. Just two equations of lines, okay? And you wanted to find a line where you knew something, for example, perhaps a slope belonging to that line, or you might know a line going through another point, and you'd say, get me an expression for a line going through this point and the same point as those two equations cross each other. So if they cross, you're looking for another one like this, something that'll cross there, and you know some other piece of information on this. It might be its slope, or it might be that it goes through a particular point. Now, what we did there was we went L1 plus some number which we call lambda L2, and you'll say that's equal to 0. Now technically, as I was saying, that's 0 plus 0 equal to 0, but fundamentally out from this nice little thing you can get an equation of a line. There's almost exactly the same thing now about to happen in the last section on the circle, so it won't take long to go through this. It has to do with common tangents and common chords. If we have, for example, two circles that touch each other, I'll redraw that actually. I'll draw it bigger to make it more sensible. Two circles touch each other. Now they can do it by having a common chord, which is this bit in the middle. The other option is that they can touch each other just at a single point. And under that circumstance, they have a common tangent. Okay? Tangent or chord. What do? Almost the exact same little game is played again. What we're going to do is we're going to just name the two circles S1. Well, I'll draw it where I have slightly more room. We'll call them S and S1 because that's what he has. S is equal to x squared plus y squared plus 2gx plus 2fy plus c equal to 0, and the other one, S1, is equal to you'll notice in the one that has a 1 here, to tell it S1, you have a G1, you have an F1, and you have a C1. So basically we have two equations. If we take one equation away from the other, what we get is S minus S1 equal to 0. The reason it's equal to 0 is S, you can see here, it's equal to 0, and the S1 is also equal to 0, so 0 minus 0 equal to 0. Let's just see how this works. It's actually a quicker method than the one for the line. Now what we want to do is to go s minus s1. And what we will find is that, and this is the trick about it, the x squareds cancel each other and the y squareds cancel each other. So you're going to be left with an expression which will only have x to the powers of 1 and y's to the powers of 1. And that's a line. So the answer to this turns out to be x plus y plus 1 equal to 0. Because these things cancel. It means the expressions for the two circles cancel out their x squareds and their y squareds, and we're only left now with x to the powers of 1s and y's to the powers of 1s. So you finish up with a straight line. And the interesting thing is, having taken 0 from 0, that straight line will be the equation of a common chord if the circles touch at 2 points, or it'll be a common tangent if they touch only at 1. Now the thing is, that's the end of that chapter. Because there's only a few concepts, generally what happens is the questions are bitty. You get things where some constant is not given to you and you have to work your way around it. But the rules in this particular chapter, the things you appeal to, such as perpendicular distance, you find are the same things that you've been using in the equation of the line. You will also find that these same little rules get used a lot when you're dealing with calculus and when you're dealing with trigonometry and a number of other sections. So it's really worth your while to practice and do a lot of practice until you get very familiar with these particular ones. Just a little concept which I think we covered before, and that is, very often we make a mistake when we go to study something, and the mistake is, having looked at it, we can say, this is very hard, so I can't do it, obviously, is the conclusion. The truth is, most of the time, that we're wrong. And we're wrong because we confuse two things that are different from each other. Only a very small amount of time, when you look at something, is it really hard and that you need help from another. Most of the rest of the time, what you're looking at is just not familiar to you. And what you do is, you persist with it, and it becomes familiar, and then you realize it's quite easy. If you say to your mind, when you look at something to begin with, you say, it's not familiar, the mind then immediately thinks that if I work at it, I'll understand it. Whereas if you keep telling your mind, this is hard, it keeps believing it can't do it. And you just finish up not really pushing that extra little bit that would have allowed you actually solve the problem and learn the piece. So these particular sections, the last one we looked at, which was the line, and this one, which is the circle, fall into that type of category. They're bitty, and because they're bitty, we can easily consider that they're hard, and they're not, because the rules are very basic. And play around with a lot of the questions. Get good at it, because then lots of other sections become much easier for you. Okay. Bye now.